8.
S1 of tail. Vania?
2.
2. Okay. So now let's think about any interval in the real line. Can you give me an interval, please? So we have the real line. Say this is the real line. Think about any interval. Give me the limits of the interval. Gabriela. Gabriela, what is your favorite number?
18.
Okay. That's great. Okay, let's say this one. And let's compute the pre-image of this interval. 18. This is the set of omegas that belong to big omega 3, such that S1 of omega belongs to that interval. So let's try an error. For example, S1 of HHH can be in this interval. Yes or not? S1 of HHH can be in this interval. 18, 42.
No, teacher.
HHT. HHT. Vania? Is in this interval or not? Yori?
No sé, profe, la verdad.
Okay, let's see the definition. The definition of S1 is this. It will take the value of 8 if the first entry of this sequence is H. And it will take the value of 2 if the first entry of this sequence is tails. Then S1 of HHT will be here or not. Between 18 and 42.
No.
HTH What about this guy? I mean, S1 of HTH or S1 of head, tails, head can be here.
No.
Okay, no. What about head, tails, tails?
No.
And all these guys?
No.
Neither of these guys, right? So this set will be the empty set, right? This or this. So the pre-image of this interval will be the empty set. And the empty set, for sure, is an event. Okay, the empty set is an event. So there are two events that always happens. Are events. The empty set and the whole set. So we have found that the pre-image of this interval is an event. Now, to make sure that this function is a random variable, we have to prove to any interval. If this happens to any interval, then this function will be called random variable.
Teacher, I'm sorry, can you repeat the last part, please?
Yeah, sure. I said we have proved that the pre-image through this function of this interval is an event because the empty set is an event. But to prove that this function is a random variable, we have to try for any interval in the real line, any. Someone can say, okay, but there are a lot, quite a lot. Maybe I will die before I finish to try to an interval. That's true, but we can try something more clever. For example, this is 2, this is 8. We can characterize any interval in the real line. There are intervals that contain 2. There are intervals that contain 8. There are intervals that contain 2 and 8. And there are intervals like this one that contain neither of them. Okay. So there are 4 types of intervals. P1, P2, P8, P28, and B. Right? So we can characterize any interval in this line like this. Intervals that contain 2, intervals that contain 8, intervals that contain 2 and 8, intervals that contain none of them. So, for example, what happens if I try to compute the pre-image of this kind of intervals? What would you get? Minelli?
I'm sorry, can you repeat?
Yeah, sure. Can you tell me what can you get if you compute the pre-image through the is function S1 of the interval B2, where this interval B2 is the interval that contains 2 as element. So there are a lot of numbers here, and one of them is 2, the number 2. What is the pre-image? So you have to compute this. The omega such that S1 of omega belongs to can go over this again. For example, H will be in this set or not?
No.
No.
Okay, T.
No.
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 None of these guys will be in this set, right? Because S1 of these guys will be 8, and 8 is not here. However, S1 of THH.
Yes, I think, teacher, sorry, the last 4 elements are going to be in this function.
Yeah. The last 4. TH, T, TH, and TT. 6. Because this guy is subset of this guy, then the image of this guy is an event. So far, any questions about this example?
Teacher, sorry, B2 is which interval or which number? 2?
Okay, B2 is the set you intersect this set with this, you only get this.
Okay, thank you.
So 8 is not here, only 2 is here, and any other number with 8 is set such that this guy is 8, and if you want to 8 intersect is 2 and 8, and finally BMT 8 is 8. Any more questions about this example? Okay. What about this? The pre-image of B8. Ricardo, can you tell me what is this set?
I think it will be the first 4.
Okay, good. HHT, HTH, HTT, which is a subset of the sample set, which means that the pre-image of B2 is an event. Okay, what about this one?
That would be all the elements in the sample set.
Okay, so it's the whole set which is included in the sample set, which means that S1, the inverse of S1 of B28 is an event. And the last one will work like this. So in this way, we have proved any interval. Because this happens for any interval in the real line, S1 is a random variable. Just to comment this, an event for this example is any subset of, okay, and the set of all the events is set F, and in mathematics this is called sigma algebra. Now let's define sigma algebra. Sigma algebra, note, sigma algebra is that empty set. Okay. Then a sigma algebra is a set of subsets in omega such that first empty set belongs to sigma algebra F, okay, belongs to F. Second, if A belongs to F, then the complement also belongs to F. Finally, if you have a sequence of sets that belong to F, then the union also belongs to F. So when you have a set that satisfies all these properties, it will be called sigma algebra. That is mathematics. F is set of all the events. That is for us. Okay. There are two types of the trivial sigma algebra. Trivial sigma algebra. So the smallest sigma algebra you can find, we usually denote like F sub 0. This is sigma algebra that contains the empty set and the whole set. And the largest is when the sample set is finite. The largest sigma algebra is the power set. The power set, the set of all the intervals, all the subsets of omega. Okay, this is just a note. Okay. Any questions, guys? Enzo, José Enrique, Diego Alonso.
Teacher, what is the if sigma algebra?
What is the sigma algebra?
Yes, me confunde un poco.
Okay. In statistics, okay. We have some, say, elements, okay. Our keywords so far. Sample set. Just note like this. Then we have set of all the events. An event. An event is F is a subset of the sample set. That is an event. Then we have the set of all the events. For example, when the cardinal of the sample set is a integer, positive integer, so it's finite, like this one, right? The cardinal is 8. Then we can use the power set. This power set is just the set of all the subset of this guy. For example, in this case, the cardinal of this sample set is 8. Then the power set will have 2 to the 8 elements, 256 elements. Easy to work.
Okay.
But what happened when this set it's like it has infinite number of elements? Then we don't work with this set because it's not manageable. It's difficult to work with this kind of sets. So we work with something that we call sigma algebras. Actually, this guy is also sigma algebra, because these kind of sets have a particular structure, which is this one, that allow us to work and compute probabilities. And that is the next. This is also a sigma algebra. Then we have the probability. Or probability measure. Okay, and the probability measure is a function that goes from f to this. Finally, we have, because you only are able to compute the probability of any event. That's why we need to define before, to define the probability, the set of all the events. Then, so you can see that first we have talked about the sample set, then what is an event, then the set of all the events, which is a set of subsets of this guy. Then we talk about the probability, which is a function that goes from this set to this interval. So we only are able to compute probability of events. Finally, we talk about random variables. random variables. And a random variable, x, is a function that goes from omega to the real line. Such that takes any element here and becomes a number in the real line. So you see the difference between this guy and this guy, but this goes from the sample set, this goes from the set of all the events. But there is a relationship between these guys. The pre-image of any interval for any interval this should be here. Why? Because if this guy is in this set, okay, then you can compute the probability of this, because this guy is an event. There is no other way you can deal with probabilities and random variables. That's why you need to make sure that this function satisfies this property. Now someone will say, okay, but we don't do this actually. Oh, yes, we do. For example, let's say in our example, S1, right? This is the stock price at time 1. The stock price at time 1 can take two values, 8 and 2. 8 if W1 is head, and 2 if W1 omega, small omega 1 is tails. Then we want to compute the probability of any event. For example, what would be an event? I want to compute the probability that the stock price is greater than 2. What is this? This is the set. Right? This S1 greater than 2 is just the pre-image of the interval 2, infinite. Because this is the set of omegas that belongs to omega such that S1 of omega is greater than 2. And you know that if this is a random variable, this must be an event. And we can compute probability of events. We're only able to compute probability of events. So that is why it's important, this property. Now, does it make sense? Minelli? Eduardo. Yori.
Sí, profe. Todo claro.
Okay, let's go back to the slides. This is the exam. Now let's talk about some properties of random variables. Okay, any random variable or real value random variable has something that we call CDF or cumulative distribution function. And the CDF of a random variable is just the probability that the random variable is greater than a real number x. That is the CDF of small x. Okay, the CDF of this random variable x of a small x is just the probability that big X, our random variable, is less than this small x. And this function has three properties. The first one, it should be between 0 and 1 for any number. It should be monotone and non-decreasing. And also in the limits, the CDF of minus infinity should be 0 and the CDF of plus infinity should be 1. So if you want to make a draw of the CDF of any random variable, this is 0. It should be like this, or something like this. For example, this is an example of CDF. It's non-decreasing, it's monotone. In the limits, when x goes to minus infinity, f goes to 0, and when x goes to plus infinity, f goes to 1. So it should be in this range. That is the CDF. Now, sometimes these random variables has something that we call the probability density function or the probability mass function. Okay, we have two things. 18. things. Probability density function the probability mass function. Random variable. So some random variables have probability density function, and that happens for only continuous random variable, and this happens for discrete random variables. Okay, but there are some random variables that don't have any of these functions. Okay, but when these random variables have this probability density or mass functions, we can compute the CDF as an integral here or as a sum. Okay, we used to abbreviate PDF, probability density function, PMF, probability mass function. Okay, so this is the cumulative distribution function. So the cumulative, when these probability density functions exist, of the where F is the PDF. The summation where P is the probability mass function. Okay. Okay, there is an example. What is the PDF of uniform random variable? The uniform. Okay. The standard. Okay. A standard uniform random variable. Say X is 3, so like uniform 0 and 1. What is the PDF of this random variable?
Teacher, I think that is the integral from 0 to 1, and in the middle of the function, this integral is 1 divided by 1.
Okay, that is the way you compute the CDF, but the PDF, okay. I will help you. 0. And this is 1, right? 1 when X belongs to the interval 0, 1, 0 otherwise. So if you want to draw this function, it should be like this. Here. This is this function. That is the PDF of the uniform random variable. And what Diego Alonso said is how to compute the CDF. Okay, the CDF said should be the integral of minus infinity to x of this PDF. Then this integral, I can split it into two integrals from minus infinity to 0 plus the integral from 0 to x. If x less than 1, less than or equal to therefore x between 0 and 1. Okay. So x, and what is the value of the function between minus infinity to 0? Minelli? What is the value of the PDF of the standard uniform random variable between minus infinity to 0?
Sorry, teacher, I don't know.
Okay, let's look at the definition of this PDF. The PDF here of this standard uniform random variable is this one. So in the interval minus infinity to 0, what will be the value of f? It will be 1 or 0.
0.
Okay, 0. And between 0 and x, where x is between 0 and 1,
One.
excellent. The integral of 0, this is just 0, and the integral of 1 is x. In this case, is y between 0 and x. This is finally x. Right. So the CDF of this standard uniform random variable will be x. So if you want to plot CDF 0, the CDF will be like this: 0 here, then x, then 1. So this is the CDF, the standard uniform random variable for this example. This is a straight line, okay? No, it doesn't look like a straight, but it's a straight line. It's 45 degrees. So far, any questions about the CDF, PDF, PNF, how to compute the CDF from the PDF? yo creo que debemos tomarnos un descanso de 10 minutos, de tal manera que ustedes se toman un buen cafecito o un té, agua, o nos despertamos todos bien para continuar. ¿Les parece? Así yo aprovecho también para tomarme un café.
Sí, profe, está bien.
Dale.
Está bien, profe.
Ya, entonces, 10:47, ¿ok? Hola chicos, ¿qué tal? ¿Están listos? Buenas.
Sí, profe.
Muy bien, entonces ahora vamos a hablar de the expectation. Okay. But before we talk about expectation, talk about one of the probably most famous distributions, that is the standard normal distribution. Okay. What is the PDF? Okay, the PDF of the standard normal random variable. Distributes normal 0. What is the PDF of the standard normal random variable? Gabriel?
I think something like 1 over square root of 2 pi
2 pi times
exponential of x squared x squared divided by 2. Oh no, yeah, 2 squared. I think so. 2 squared, or I don't remember the part.
we're missing something here. Anyone else
Minus?
Fine.
Yes, minus.
And we also know that the CDF of the standard normal random variable cannot be computed analytically, right? You only can get the CDF in a numerical form. So the integral of this guy doesn't exist. As we sometimes call this as primitive. So we compute the CDF using numerical methods. Anyway, this is function you should know. It's commonplace in any finance application. Okay. So this is the PDF of the standard normal distribution. The uniform also is very popular. That's why we talk about the uniform distribution here. Other important distributions are the binomial, Poisson, geometric, later the T, the chi-square, so on and so forth. Anyways, okay, now let's talk about the expectation. Expectation. The expectation is just the, you can think about the expectation as a weighted average of the values that a random variable can take. When we work with continuous random variables, the expectation, and we denote the expectation using this notation, expectation x is continuous random variable. The expectation is just the integral over the real line of x times the density function of x. That is expectation when x is a continuous random variable. And when x is a discrete random variable, the expectation is the sum, the weighted sum of the multiplied by the probability that x takes the value of x all over the any x. In this case, this p, if you want, p of x, okay? Well, this is the PDF, and this guy is the PMF. Okay, this is the probability density function, and this one is the probability mass function. Okay, that is the expectation. Okay. Example, the expectation. Look at these slides. Revise some properties of the expectation. Okay, if x and y are random variables and c is a real number, then the expectation of the sum of these two random variables is the expectation of x plus the expectation of y. If c is a constant or real number, then the expectation of this constant or scalar times this random variable x is the constant multiplied by the expectation of the random variable. Also, we know that if this random variable x is non-negative, in other words, x is greater than 0, any possible outcomes in the sample set, then the expectation of x will be also non-negative. So here we have an example of how to compute expectation. For example, let x and y be random variables such that the expectation of x is 1 and the expectation of y is -1. Let's compute the expectation of this expression. What is the value of the expectation of -2x plus 3 times y plus 5? Enzo, what is the value of that expectation?
Is it -2 expectation x plus 3 expectation y?
Plus, okay. And you can replace expectation
Yeah.
of x and expectation
And
of
then-
y. So according to Jose Enrique and Abraham, that should be 0, right? Okay, that should be 0. Then we can talk about now about the moments, okay? There are two particular important moments. One is called the mean and the other one is called the variance. But the mean and the variance are related to different kind of moments. Okay, the mean is related to the moment and the variance is related to something that we call central moment of a random variable. The moment of any random variable is just the expectation of that random variable to the power m, where this m is an integer, positive integer. Okay, so if m is 1, we have the first moment. If m is 2, you get the second moment, and so on. Then we have the central moments. And central moment is just the expectation of the random variable subtracted by its mean to the power m, where m, as in the case of the moment, is just a positive integer. So when m is 1, we get the first central moment. When m is 2, we get the second central moment of x, and so on and so forth. Then the first moment of any random variable is called the location of the distribution of x. Okay. Or just the mean or expected value of x. The dispersion of the distribution can be measured using the second central moment of x, because the first central moment is 0. So the second central moment is called the variance, okay? So the variance is just the expectation of the square of the difference between the random variable and its mean. We used to denote the variance using the Greek letters sigma square. And the square root of the variance is called the standard deviation of our random variable. Okay? So now we know two more properties about the expectation variance. Of this important property, this is called the moment generating function. Okay. Let's say we have a random variable x and t is a real number. Then there is something that we call the moment generating function, and the moment generating function is denoted like this: m of x of t. And this moment generating function is defined as the expectation of the exponential of t times x, where t is a real number and x is a random variable. And this moment generating function will exist if the expectation of this expression exists. There are situations where this moment generating function doesn't exist, okay? So there are some random variables that doesn't have moment generating functions. There's another function that is called the characteristic function. The characteristic function is similar to the moment generating function, okay? But instead of having just exponential of t times x, you will have exponential of I times t times x, where this I is the square root of -1. So we enter to the world of complex numbers. In that world, that function always exists. Now, why this function is too important? Because we can characterize entirely a random variable using this moment generating function or the characteristic function. Why is important for us to characterize the random variable? Because if you know how the random variable behave, you can know everything about an event that can be described using that random variable. Everything. Because you know the entire distribution. You have the mean, the standard deviation, any moment, because you know the entire distribution. Sometimes we deal with distributions that can be characterized by some parameters. For example, the normal distribution can be characterized by 2 parameters. We only need 2 parameters to characterize the normal distribution. What are those parameters?
Mean and variance.
The mean and the variance. If you know the mean and the variance, you know everything about the normal distribution. You can do anything with that. Compute percentiles, quantiles, whatever you want. Okay, but there are some random variables that needs more than 2 parameters to be characterized entirely. Three, 4, 5. Anyways, but one way of characterize a random variable is using the moment generating function. For example, if let's say you are working with some random variable, okay, and you need to get some properties about this random variable, but you don't know the distribution of this random variable. And let's say you know the distribution of other random variable, and through some transformations, you can get from that other random variable to this random variable. Or you can, or you're able to find that the moment generating function of that random variable is the same that the moment generating function that a random variable you already know. So that's it. What that happens, you can say for sure that the distribution of those random variables are the same. And the problem ends because you know everything about that random variable that you wanted to study at the beginning. That's why the moment generating function is very useful. I will give you an example as an exercise at the end of the class. Okay. Anyways. Okay, there is an exercise here. Let's say x is let's x be a random standard random variable, compute its moment generating function. You can compute it, or you can go to Google it. Copy that moment generating function. Okay. Let's moment if you type moment generating function, this is what we were talking about. This is the Bernoulli distribution, for example. This is the distribution. This is the moment generating function, and this is the characteristic function. Then you have the normal distribution. This is the moment generating function of the normal distribution, with mean, mu, and variance sigma square. And this is the characteristic function. But there are some distributions, for example, the Cauchy distribution with these two parameters, mu and theta, where the moment generating function doesn't exist, but its characteristic function exists. As I said, the characteristic function always exists. Sometimes the moment generating function won't exist. Okay. Let's go back to the slides. We have two other moments, or two other measures, the skewness and kurtosis of a random variable. The skewness measures the asymmetry of a distribution, okay? And it can be computed as the third central moment scaled by the cube of the standard deviation. And the kurtosis measures the tail heaviness of the distribution. What does it mean? It measures how likely are the extreme events. For example, an extreme event can be a crisis. How likely are crises or financial crises in the markets? And the kurtosis can be measured, or it will be computed as the fourth central moment scaled by the square of the variance. Okay. So comments, the normal distribution has a kurtosis of 3 and a skewness of 0 because it's symmetric. The normal distribution is a symmetric distribution. Okay, we will talk about this. We have the joint distribution. We talk about the joint distribution. We're trying to deal with random variables that are related in some way. Not only one random variable, but 2 or more random variables. Let's say we have 2 random variables, x and y. The joint CDF, now we have this called this thing, the CDF, but now the joint CDF of these 2 random variables is just the probability that the first random variable x is less than equal than small x, and the second random variable y is less than this small y. And we denote it like is f of x, small x, comma, small y. Okay, and as before, sometimes the PDF and the PNF, or joint PDF and joint PNF, exist. And when those functions exist, we can compute the joint CDF as just an integral of the PDF in the case of continuous random variables, or just sum when we deal with discrete random variables, or a mixture if we're dealing with one random variable that is continuous and the other one is discrete, you will have an integral and the sum here. Okay. So this guy, small f of u and b, is the joint PDF of x and y. Then the CDF of x and y, which is the same as this one, is the integral, the double integral from minus infinity to x and y of the PDF, the joint PDF. Then we have the marginal distributions, and the marginal distribution is also the double integral. But in this case, one of the integrals will go all over the real line. For example, if you want to compute the marginal distribution of x, the integral in the other random variable will go from minus infinity to infinity. So this integral is for the for this guy p, which is related to the random variable y, because you want to compute the marginal distribution of x. And if you want to compute the marginal distribution of y, the other the integral will be over the values that x will take. Okay. This guy, this guy, comments. This guy. This is called the marginal distribution. Okay. Then this is called the marginal density function. And this is the marginal distribution. So the marginal distribution of x is the integral from minus infinity to x of the marginal density of x. Okay. Then the most important concept when we deal with many random variables will be the conditional distribution. This conditional distribution is something new that we haven't talked about when we are dealing with just real value random variables. The conditional distribution exists when we deal with two or more random variables. Let's say we have two random variables, x and y. In this case, discrete random variables. Then the conditional distribution or the conditional PMF of y given x, given that x takes this value xi, and we used to write that conditional PMF as probability of y is yj given is given that x takes the value of x, small xi, is the joint distribution or joint PNF of x and y over the probability that x takes the value of xi. This probability in the denominator of this fraction is just the marginal distribution of x. Okay, so you have the marginal distribution here, and here you have the joint distribution. So this is the definition of the conditional PMF. When we are dealing with continuous random variable, you have something similar, but in this case, instead of having a PNF, you will have a PDF. The conditional PDF, and with another like this, is just the ratio between the joint PDF over the marginal PDF of X. Now, so far, do you have any questions about the conditional distribution, marginal distribution, joint distribution, and the relationship between those concepts? I believe you need some examples or exercises, right? In order to like understand those concepts properly. I will talk to Gonzalo to work with some of these examples. Okay. To talk about the conditional expectation, concept of independence. I think we need more time to talk about these concepts, but we go over those slides next lecture. Please revise the missing slides and finish the view of stats the first hour of the next lecture, and we can start to talk about Monte Carlo. No tiene ninguna otra pregunta, ¿no, chicos? Gabriel, José Enrique, Abril. ¿Todo bien?
Sí, profe, todo bien.
Sí, primero todo bien, profe.
Ya, entonces, ¿cuándo tienen la recuperación con Gonzalo?
Me parece que el lunes.
Lunes en la noche, creo.
Ya, bacán. Bueno, entonces ya el miércoles nos vemos, continuamos con esto. Terminamos esto y arrancamos con Monte Carlo. Porfa, revisen los slides de esta clase y la siguiente.
Profe, en la mañana tuve problemas de conexión justo al comienzo de la clase. Creo que me puse ausente.
A ver, ¿cómo te llamas tú?
Fernando.
Fernando. Ya está. Ya, bueno,
Gracias.
entonces lo dejo. Tengan un buen fin de semana. Repasen. Y voy a compartir la pizarra, Juan Enrique, no te preocupes. Ya creo que ya, a ver. Es más, lo voy a poner ahorita. Ya está.
Gracias, profe.
Listo, chicos. Conversamos.
Profe, yo creo que entré como que 7:45. Creo que me había puesto 60, también creo.
Yori,
Profe.
cuenta. Listo, abre,
¿Sí?
cuídate.
Igual.
Me
profe.
escribiste, pero...
Disculpa, no escuché.
Yori. Me escribiste, creo.
Sí, profe, pero Gabriel le dijo que le acaba de decir algo correcto. Creo que él se conectó un poco tarde y quería saber si le podía poner.
Sí.
Ya. Ok. Ya está, entonces. Listo. Tengo un buen fin de semana, entonces, chicos.
Igual, profe.
Cuídense.
Profe, sí,